So we did some basic population simulations, right? And sort of the core reason we were doing that was to get familiar with using for loops. But I also want to sort of extend this now and to get into a bit more of an example of why we would do computers, because what we did before, we could have done that in Excel, easy peasy, right? If you're more comfortable in Excel, cool. Um, I want to extend things into a bit more of a complicated regime, and let's see if we can do that. So let's start with a relatively simple concept. Let's start with predator and prey, right? So we have two animals, two populations. Now, these again, I can't help myself. It's bunnies and foxes as far as I'm concerned, right? But this sort of effect has been shown in everything from microorganisms to macroorganisms, right? And this is the interaction between predator prey and some pretty unusual effects that can happen. Okay, so let's start. Always, we're going to specify our populations, some population variables. So let's say prey pop. So for our prey population, and this is initially going to be something like 0.1. Okay, and then our initial predator pop is going to be the same. Whoops, C 0.1. All right. So let's have a think about how our prey population would change. This is going to all sit in a for loop eventually, but let's try and think. So our prey population, okay, at time t plus 1 is going to be equal to, our prey population at time t plus our prey population at times t times some birth rate, right? Let's call that prey birth rate. Okay. Now, right now we have done nothing new. Let's set this to be something. We can't set this to be too big um, for maths reasons. Let's go 0.0.2. Okay. So our prey birth rate is 0.0.2. But we've got this predator and prey. So we're also going to sort of subtract off something, right? And this is going to be minus our, well, what should it be? It should be like the predator population. Actually, I've done some slight mistakes here because I started this with prey. This should be like this. Pop. Pop, not population. All right, so this should be like pred pop at times t. Whoops, at times t. Okay, so if there's lots of predators, they're going to hunt lots of this prey. But then I also think it should be the affected by the prey population as well, because if there's like rabbits all over the ground, then it should be quite easy um, for the predators to find them. So we're going to then multiply that by the pred rate. All right, so this is how our prey population. What are we going to see? Say our predation rate is going to be, let's say this is 0.0005. Okay, so I know I typed a lot, talked a lot. Let's just expand this a little bit so we can see it all, right? So we're saying the prey population next year is equal to the prey population this year plus however many new prey were born, right? So the prey population times their birth rate. So that's just what we did before. But now we have this new term, which is about how quickly they're being eaten. And we're going to say this is the predator population, which makes sense, right? More predators, more eating of prey, times the prey population. That also makes sense, right? If there's lots of prey, it should make it easier for the predators to find them, times the predation rate. Okay, so now how is the pred pop going to change? Well, I think we're going to start with the same thing we've done everything else, right? Next year, we're just going to have the same population we had. But what is going to happen to them? Well, they are not going to grow by themselves, right? If they are left alone, if they are isolated and left alone, they will die off because they need the the um the prey to eat, right? So they're going to have a death rate with no, this is just, we're just considering one aspect of it, right? So we're going to say they have a death rate. Let's call this, we can call it the, let's call it the pred, what should we call it? We'll call it the I don't want to call it a growth rate, but it is a growth rate. It's just a negative growth rate. Let's call it death rate. All right. Pred death rate. Um, and we're going to say that is equal to 0.002. Right. Oh, I've done something wrong then. Well, and so then that is the, I'm just going to copy and paste this. This is the pred pop at times t times the pred death rate, right? So this is how many animals we're going to lose from this predator population if nothing changes, right? The population is just going to die away. But then we're going to add some animals, right? So this is how many new predators do we get for every single sort of rabbit that they catch, all right? So that is going to be, let's call this pred feeding rate. And this is going to be the pred population at times t, because after all, if we're talking about new predators being born, well, they've got to come from somewhere, right? So the more predators there are, the more new babies they should get. But of course, this feeding rate depends on the number of prey, right? Because again, just like before, if there is lots of prey, I've spelled that wrong up there, prey pop times t and prey pop times that, right? So there's our whole thing, all right? So we say the predator population next year is equal to the predator population this year minus the predator population times the pred death rate. So this is how many die each year, because then the natural death rate, the population by itself without any food to eat gets smaller. But then how many get added every year? Well, that's the predator population times the prey population times the predator feeding rate. And we can notice a certain symmetry in these equations. All right, and then we just need to set up our for loop properly, right? So we're going to say T max, and we're going to run the simulation for a little while because it's going to do something a bit more interesting than your average one. Let's say we run it for 10,000 years, and we say for T in 1 to T max, we do that same thing, minus 1. We open our curly brackets, we go down there, we close them, and fingers crossed this works. There's a good chance it won't. We'll see. We'll run the source. Aha, I did a mistake. What is it not like this? Oh, too many brackets. 40. There we go, right? So there should be one for every time you open a bracket, you need to close one. So we're opening it for the for loop, and then I had another brackets for the tmax minus 1, and we go source, and that ran fine. All right, so then let us look at the plot, and I think I can just go prey pop, and here it is over here, and my goodness, what is going on? Look at the population. We get this exponential growth, and then it peaks and falls off, and then it stays low, and then grows, peaks and falls off. What happens if we, so that's the prey. What happens if we do the predator population? Well, here it's sort of the same thing, but inverse. It sort of grows instantly and then slowly drops off, and grows instantly and slowly drops off. Isn't that bizarre? Okay. Now, what I can do is I'm just going to do a little wee graph for you, and you don't need to know how I'm doing this, but I'm going to go par mf row, I think is right, equals C, and I want a 1 by 2, and then I go plot the pred population and plot the prey population, and there we see them side by side. And so we can now easily see that what's going on is the prey population starts to grow first, right? So here we are in this early 2000, before 2000, year 2000, and it grows and grows and grows and grows. And then right about, yeah, at about the year 3000 is when this peaks, and then the predator population grows massively. And that massive growth of the predator population is what then causes the prey population to flatline. And then, of course, there is no prey, so the predators die at this rate that we specified here, where they slowly all die off, and then their death allows the prey to grow back, and we get this oscillation. Now, there's a whole bunch of questions we could ask, right, about this equation that we have, this simulation that we have made. Is this oscillation that we witness because of this parameters? You know, what happens if I change them a little bit? Let's change the prey birth rate to 1. All right, and actually what we can do is we can just copy this code from here, paste it at the bottom here, delete those little things at the beginning. Okay, and so I change that to 1. Are we still going to see oscillations? Let's see. Source. Well, we got one peak in decrement, but maybe so this prey birth rate says how quickly this happens. All right, so what if I change that up to 0.1? There's a chance I could do something bad here, but let's see. No, now we get a couple of oscillations and one almost about to happen. Okay, so that's kind of interesting. That's interesting. That's interesting. Let's set it back to where we were. What is going on? All right, so now we enter some times where we really want to be able to investigate this system, right? And I want to add, right, these equations weren't just invented by somebody trying to teach somebody R, right? Somebody was trying to explain a real life observation in terms of prey and predator systems, and they couldn't understand what was going on. Um, and so they invented this equation that they thought was a reasonable assumption of the real thing, and they saw this behavior and it did explain things, right? But you know, we've still got this question of what about the initial conditions, right? So we've got these rates. What happens if we choose a different initial condition? So let's say we start with a prey population of 50. Okay, what happens if I do that? Well, it looks like the oscillation is still going on. It's a bit hard to be certain, all right? So we're in this kind of awkward position. We've got this interesting behavior. We don't really understand it. What can we do? Well, what we should probably do is systematically vary these starting conditions, all right? Because the curious thing about these kind of equations is starting conditions are not just starting conditions, they're all conditions. And what do I mean by that? I mean, the behavior of the system never, it doesn't have any memory of what happened 100 generations ago. All it looks about to calculate the next time point is the previous time point. And that's the same whether that previous time point is the first time point or the millionth time point. So the behavior at different starting conditions actually describes the behavior at every kind of condition. Now, so I've actually written this code previously so that we don't need to write it all out. It's a little bit complicated, population dynamics too, but it still fundamentally has the same equations in here. And when I run source, we're going to see something hopefully a little interesting. All right, what are we seeing here, right? So this is a phase plot. It's showing how two state variables, two variables that describe the system, how they change in relationship to each other. And so what we're plotting here is, so pred P0, this is the predator population at the start, and this is the prey population at the start, right? And we started at 0.1, 0.1. So our original starting point was about here, I think. And then these little arrows are showing us how we're changing. So it's saying if you start with 0.1, 0.1, we have this little arrow are going kind of up this way. So it's saying the prey population should start to grow. But if we follow these arrows around, we see how this population will evolve. And you can see we get this interesting kind of orbit. Orbits around and around and around and around. And if we look closely, we see we have a little bit right in the middle here at point 2, where it looks like this is where everybody is orbiting. Okay, it looks like this could be stable because if we see, right, if we had started with prey, let's say 1, no, predator 1 and prey nearly 6, we would see that instantly what would be happening is the prey population would be growing and the predator population would be growing. If we started over here, we would have prey population dropping and predator population growing until again we'd reach some point and they'd go around and around and around. But it looks like right here in the middle at 2, 2, nothing changes. So let's go back to our thing here and see if this is true. Where are we? Here we are, and we're going to say our initials are 2 and 2. And let's see what happens if we run this. Well, I'm wrong. Let me go back to that figure. Oh, wrong one. Oh, because I've got different variables in here. I've got different growth rates. Hang on. So I've got 0.02 and 0.01. 0.0, 002, 001. 002, 001, 002, 001. And that's the feeding rate and the predation rate. Feeding rate. All right, good. Okay, let's try that again. There we go. Perfect flat line. That is the stable population, right? Now, what the hell am I talking about? What does this have to do with biomedical research? Okay. We have learned in the course of this module basic R syntax. We know how we create a variable. Okay. We say, my var, this, 45. We've made a variable. We know how to make vectors, right? So we can say, say my vec c345. All right, good. And we can access them by my vec2. Gets us 4, the second element. All right, we talked about data frames. I'm sure I've got a data frame in here still. If I go head df, what have we got in here? We've got the data used to make that oscillating figure, right? And so we can access the data frame with the $, data frame pred p0, and we get a, maybe it doesn't like that. Let's go d pred. Oh, because I've put a percentage symbol, not a $. There we go. Boom. Okay. And we also can access data frames with the square brackets where we can say I want the first row and the first column and I should get 6. Okay. We talked about a bit more syntax in there, and then we talked about for loops, how we can iterate through a list. We iterated through a list and we used that to compute a little simulation of exponential population growth and exponential savings growth, and it wasn't that tricky. Then I was like, all right, we're going to make a slightly more complicated system here. You don't need to know the details, though I went through the details. You don't need to know the details of any of them. You need to know the syntax that we used to generate them. And what they were is motivating examples of why this kind of stuff is so powerful, that we had this system of oscillating populations between predator and prey, right? That got people Nature publications in 1925, just for the record, okay? So, it was a big deal in 1925. God knows how they worked with the maths in 1925. I do not know. It's actually quite complicated maths, even for real people, real mathematicians. You then, I then did some secret maths secret program, and I didn't need to show you, where we saw this phase plot of the two populations changing. And from that, we were able to pull out something interesting, which is that there is a stable point at 2, 2 for the certain, given those parameters. You might want to guess if it has something to do with some ratios between some certain constants, which I'm certainly assuring you it does. But the point was, this shows the power of this, right? If we were just doing this in Excel, it would have taken a million years for us to make that state plot to find out that there was in fact a stable population, that the oscillations don't necessarily exist. And in fact, if we get a little bit away from this, they stay small. Let's just do this, 1.9 and 1.9, right? And if I run this, we're going to see very little oscillations. They don't look that little, but look, they're only going between 1.8 and 2.15. So they're very small around a fixed point. So we've seen the power of these kind of simulations, right? And these kind of simulations are used all over biology, biomedical research, not just in populations, but in how neurons behave. As I alluded to Hodgkin and Huxley, who described the action potential with a set of equations pretty much identical to what we just did. There's been a lot of work in how gene networks interact, and really how anything changes over time is well studied in these kind of equations. And there's a lot you can go down this road to try and understand the dynamics of systems. But really, we were here just to understand some simple R syntax, and we're going to build on that in the coming weeks. But hopefully we saw the power of simulating things in R and the interesting results you can get with just a couple of equations.